Okay, let's get started. Thank you very much, everyone, for joining. Good morning and welcome to the Institute of Water Chemical-Free Drinking Water Treatment and Distribution webinar. My name is Rose Schisler and I will be hosting the webinar this morning. I work for Anglian Water in the Brand and Communications team, and I'm part of the Institute of Water Eastern Area Committee. For those of you who are new to the Institute of Water, it is the only professional body that exclusively supports the careers of anyone working in the UK water industry. If you aren't a member already, I would definitely recommend it. Membership ultimately offers people who work in the industry the opportunity to broaden their knowledge and develop within the sector, regardless of their qualifications or discipline. I'd like to welcome our presenter this morning, Natalie Lamb. Natalie is a PhD researcher in the Innovation Discovery team at Anglian Water Services and the Water Research Group at the University of Sheffield. She's doing her PhD in Civil Engineering and Microbiology. Natalie is also our Institute of Water Eastern Area Rising Star for 2020, so a huge congratulations, and a member of our Institute of Water Young Persons Network. Thank you all for joining this morning. We have a great variety of delegates on, and I'd like to reassure our non-academia colleagues that Natalie has written this presentation to be pitched at an industry level. You will have the opportunity to submit questions to Natalie by typing them into the questions pane on the control panel. You may send in your questions at any time during the presentation. We'll collect these and address them during the Q&A at the end of today's session. The final note from me is that the presentation is based on Natalie's experience in research and is her own views, not those of Anglian Water or the University of Sheffield. And without any further delay, I'd like to hand you over to Natalie. Welcome.
Hi, everyone. Firstly, I want to say thanks so much, Rose, for your introduction. That was great, thanks. And also, hello and welcome to everyone here today. I've never delivered a webinar before. It's quite strange in that you can't see your audience, reaction, but I also quite like the mystery, you know, am I wearing a suit? Am I in my pajamas? Nobody knows. I quite like that. That's pretty cool. So we're here today, like we said, to talk about the chemicals that are used to produce water. Now, chemicals are used to produce excellent quality drinking water, both today and in the past. So one of the first recorded uses of the use of chemicals to drinking water was actually in 15,000 BC. The Egyptians used alum for coagulation to help particles stick together and settle out in drinking water. And they actually know this from hieroglyphics in ancient tombs. So chemicals have been used for a really, really long time. And actually, chlorination is a real big one. It's been regarded as one of the major achievements in public health improvements ever. So the first recorded use of chlorination in the UK was in 1897. So there was a small town in Kent that was suffering from a typhoid outbreak. Chlorine was used for the first recorded time to disinfect the water main that was supplying this drinking water, and the typhoid outbreak got better. And since that time, we've been using chlorine an awful lot. It's actually been found since its introduction in America to have reduced incidences of cholera by 90% and typhoid fever by 80%. So what I'm basically saying is these chemicals work. They've been used in the past, they've worked in the past, they work today. And our drinking water quality here in this country is really, really excellent. But is the same going to be true in the future? So in the future, there are all sorts of challenges that are going to face us. And this is just our best guess at what some of the challenges might be. The current situation with the virus is an excellent example of something we didn't necessarily think was going to be happening to us. I certainly didn't predict it anyway. And just out of these challenges that are here, climate change for me is the real big one in terms of me and my research and the work I do. So climate change and its impact on water and quality, it's probably going to decrease it's going to deteriorate the source water quality. So that means rivers, it means groundwater sources. All of these are really going to be impacted by climate change in future. We might have to find new sources of water. We might have to put a lot more treatment steps in place to get the same quality of water today as what we will need in the future. But to tackle these sort of long-term challenges that are going to take place in the future, we really need to start doing some long-term work, sort of looking at goals, really big goals in future. And I think that's where my research is really helped, because obviously we're not going to be turning off the chemicals tomorrow in people's drinking water. We're quite a way away from doing that. And it's this collaboration between academia and industry, I think that's really going to help us tackle these really long-term challenges. We can no longer think in terms of driving efficiency in the next 5 years. We need to be looking a lot longer if we want our water to be sustainable for future generations. So this in the UK is where I'm working. So the University of Sheffield is where I'm doing my PhD, like Rose said, and Anglian Water are the company who are sponsoring my research, and I'm based with them as well. So the shaded areas on the map is where Anglian Water supply water and or sewage services. Within this Anglian Water region, there is a place called Newmarket, which is actually famous for its racehorses. So you may or may not know it from that. Now, this small town of Newmarket, known for its racehorses, for me in the water industry, I know it for its really good quality groundwater sources of water. So it's got naturally really good quality water, lots and lots of different groundwater boreholes. But what Anglian Water are using this area for right now is, so imagine for a second you're on a supermarket high street. So you're walking down and you're going past like Primark, you see a New Look, you see a H&M. They are putting their best items, their best products in the window to attract your attention, to draw you in, and so you can have a look at the great things that they're doing throughout their company. Now, Anglian Water are doing the exact same as that in this area of Newmarket. So they are showcasing their latest innovations, all their new research, some really interesting things in my personal opinion, things like robotics and VR and drones. That's sort of my area that I really enjoy, that sort of thing. And this is where it's like a test bed for research and innovation. It's really showcasing what the company can do. And as part of this shop window program, because that's what it's called, they have these 7 aspirational aims for what they want the future of drinking water to look like. And you can see here things like 100% customer satisfaction. That means that no one ever complains on Twitter, ever. And you've got things like 0 pollution, 0 flooding, no leakages and bursts. These are real long-term aims, and I think it's great that a company like Anglian and other companies are doing similar too. But I'm most closely working with Anglian. I think it's amazing that they've got aims like this and that they're striving to improve their drinking water treatment, their sewage treatment services in this way. And you can see here my favourite of the 7 aspirational aims, of course, is chemical-free drinking water treatment. So I started my PhD with the University of Sheffield and Anglian Water, and I sort of asked what my topic was going to be. And they gave me this topic of chemical-free water, and I could sort of take it whichever direction that I wanted to. This presentation today is an exploration of sort of the things I was thinking, what I wanted to do. I had to do some sort of experimentation, something new, something novel, a new contribution to knowledge as part of this work. But what specifically could I do in chemical-free water without actually turning off the chemicals in water today? Now, as a business, this is what chemical-free water means. Now, I've said chemical-free water quite a few times, but actually what I'm referring to is 100% compliance in chemical-free drinking water treatment and supply. It's not the catchiest phrase, so that's why I've been saying chemical-free. So I am talking about treatment and supply, something I'll go into in a bit more detail shortly. And the reason why 100% compliance is there is because, yeah, we could easily turn off the chemicals, but we would be breaking a whole load of regulations. We don't know what would happen to people's health. We just don't know. We just would not do that in any way. And this is why it's such a long-term aim, because it's definitely not something we do today. And it's even more important, I would say, to get that compliance looking healthy than it is to turn off the chemicals. So as a company, chemical-free water really means looking at what other countries are doing who use fewer chemicals than us today, that have the same or better compliance than us today, and learning how we can use things that we can learn from them. How can we improve our services? So that's really what it all is about from a company perspective. So why are we actually even doing this research? Like I said at the beginning of the presentation, these chemicals work. And they've worked for a really, really long time. I mean, if the Egyptians were doing it, why can't we carry on doing it? Well, there are problems with our use of chemicals as an industry. And I think if we're really looking on how to make our water safer for generations and generations of people to come, then these are factors that need considering, as well as other things such as leakage, mains failures, that sort of thing. So some of the problems of using chemicals can include damage to the environment, public health concerns. Dosage is not always as optimized as it maybe could be. Some of the chemicals have unknown long-term availability, and chemicals are expensive. Now, this is very wide, very broad. So instead, I'm going to be telling you about some examples of chemicals and some of their specific disadvantages in future. I think that would be more helpful. So how are chemicals used to treat and distribute drinking water? So I think of water treatment and water distribution as two separate things. So for a start, water is abstracted from, it could be surface water, it could be groundwater from deep within the ground, like from wells, and then it is treated. Now, water treatment at a water treatment works, there are lots and lots of, there's so much research, there's a wealth of research in this area. There's a lot of alternatives out there. There are so many products on the market, and there's just so much innovation that's been done in this area. So for instance, just picking up on one of those ways of treating water, disinfection. So the reason why we disinfect water when it's abstracted, say, from a stream, is to reduce the counts of microorganisms, reduce the viability of microorganisms before it is then distributed. So one way of doing that is using chlorine or chlorine-based disinfectants, but there are lots of alternatives out there. There are things like UV light treatment, there's things like different types of filtration. There's lots and lots of different methods of disinfecting water. We've not just got to use chlorine. Now, the other way in which chemicals are used to treat water is for water distribution. So this is the pipes that lead the water from the water treatment works to the customer tap. Now, chemicals are added specifically just before the water goes into this pipe network to protect it on its journey in these pipes. And at some areas, there's even booster chemicals added because the pipes are quite long. So why are we specifically adding these chemicals to protect the water in the pipes? It's because of how long it takes for water to get to the customer tap, to get to your tap. So in some instances, sort of the average can be sort of 2 to 3 days, which I personally, as someone who drinks a lot of water and didn't really know much about the water industry a few years ago, I thought that was a really long time. When actually in the extremes of the network in the whole of the UK, it's found to be sort of 5 days, 7 days before the water reaches your tap from when it leaves the treatment works. Now, this is certainly not the norm, and this is definitely the extremes of the network, but that's how long it can really take. I would sort of work on an average of sort of 3 days, but even so, 3 days is a lot longer than what I was expecting. So these chemicals are added to make sure that the quality of the water leaving the treatment works is the same as the quality of the water entering your tap. And in this area, there's not that much research. There's not as much work done as in water treatment. And there are not many alternative things that we can be using. So when I started doing this research, I looked at water treatment. I really researched it a lot, and I saw that there was so much out there. And then I looked into this water network, the distribution side of things, and there really wasn't a lot. So I decided for my research and for this presentation to really focus on water distribution, because I feel like there's a lot of area for growth here. If you pardon the pun, because I'm a microbiologist, you know, there's a lot of work that can be done there, and there's not that many alternatives out there. So I decided to focus on the chemicals in the water distribution network. Chlorine. So I said I was going to give you a few examples of some of the chemicals that we use to treat water, or specifically for water distribution network perseverance. Now, chlorine is generally can be dosed twice in part of water treatment. So it can be done as a primary disinfectant. So where it said disinfection in the box in the previous slide at the water treatment works, chlorine can be used for that, and chlorine-based sort of other disinfectants based on chlorine. And then chlorine can also be used just to go into the network. I'm talking about the one that's going into the network, the secondary dose of chlorine, otherwise known as a chlorine residual. So the purpose of using a chlorine residual is generally to stop regrowth in the pipe network of microorganisms. However, it has been vastly studied and found many, many times that microorganisms can and do grow in the pipe network. However, I must additionally note that the vast majority of these microorganisms alive in the pipe network, or surviving in the pipe network, I should say, are harmless to humans. If you think about it like a Yakult yogurt, there's lots of bacteria in there. They famously publish how much bacteria there is in a Yakult, but you drink it because it's harmless bacteria. And that's what the majority of the organisms within the pipe network look like as well. Just think of it as a Yakult, but in much less quantities of bacteria, I guess. Now, there are other problems of dosing chlorine. One of them is sort of customer perception. So if you go somewhere else in the UK, you can sometimes notice the difference in chlorine, or say if your local area, they've increased the chlorine a bit, you can really taste it, you can really smell it. A few years ago, I went to America and it was really strong. It smelled like a swimming pool in that glass of water. And that's actually because in America, they can use 3 times the dose of chlorine than what we're allowed to use in the UK. So it can be much, much stronger than what we're used to. Also, you know, when you go swimming in a swimming pool and you get sort of red eyes, there are people who have that when they're drinking tap water. So I've seen quite a few videos of people they say they're allergic to water, and I was quite intrigued by this, but they could actually be allergic to specifically tap water, and even more specifically, they're just hypersensitive to the chlorine in their tap water. So this really impacts their day-to-day life. For instance, they can't go and shower in their own house without having rashes, eye problems, all sorts of problems. So there really can be an impact of dosing chlorine on people. Even though the amounts that we're using is so small, some people can be hypersensitive to it. And some people can really notice the taste and the smell when things change in the chlorine dose. Another problem with the use of chlorine is that it has the potential to form disinfection byproducts when it comes in contact with organic matter. So an example of organic matter is if you have a river and a leaf falls in that river. That river will break up that leaf eventually, and then that water contains organic matter. So it's naturally occurring, and it comes in contact with chlorine and forms these byproducts. In high concentrations, they've been found to have a health impact. So that's an additional negative there. Another disadvantage of chlorine is chlorine was a substance that was used to form mustard gas in the war. It's a hazardous material. I mean, yeah, the amount that we're dosing at the customer tap, that's absolutely nothing. It's not going to have any sort of impact in terms of that. However, producing chlorine, transporting chlorine, that's where the risk really lies, storing the chlorine. So for instance, in South Carolina in 2005, there was a train derailment. The train was carrying chlorine. It resulted in a chlorine leak, and 9 people sadly died due to it. And a whole 1-mile radius from around the train derailment, there was no form of life. So all plant life even died. So it just shows you the impact that it can have, not just on people, but also on the environment. So chlorine, it does do its job. It really protects us, like I said in the beginning, for sorts of things like cholera and typhoid. And as I said, it is regarded as one of the major achievements in public health improvements. But equally, when we're thinking long term, we're thinking about how can we possibly make our water even better than what it is right now. I think it is a consideration. And many people, when they speak of chemical-free water, chlorine is the real thing that comes to mind first. Now on to another chemical, phosphate, also known as orthophosphoric acid or phosphate, orthophosphate, but I'm going to be calling it phosphate for this presentation just because I feel like it's easier to say and it's easier for listeners to hear it. So in terms of phosphate, why am I discussing this? Well, for a start, I'm going to have to take you back and discuss lead. So lead is really cheap, it's malleable, it was easy to use. So in fact, the Romans used it for their pipes, for their drinking water pipe system. And it does the job. It's very good for transporting water. However, what they didn't know is the health impact that lead can have. So lead accumulates in your body over the whole course of your lifetime, in your bones and in your teeth. But before it gets stored, what happens is it gets transported in your blood through all of your major organs. Really, really, really high doses of lead can actually cause death. And then all of the organs that it's being circulated to, they can almost be attacked. So like the central nervous system, all of the major organs, they can all be impacted by lead. But I think most noticeably in literature and research is the impact it has on children, particularly young children. It really impacts their mental health development. Like I said, it's being circulated in your body before it gets accumulated. So yeah, it really has an impact on children, but to all humans, lead is of concern. The World Health Organization say there is no safe level of lead concentration to have in your blood at all. So it is of concern. Back to the Romans then. So they were transporting their water through these lead pipes. And some people even suggest that the lead used in the pipework did cause the demise of the Roman Empire. It is of major dispute because actually they ate more lead than what they put their water through, because it's quite sweet. So they use it as a sweetener in wines and meats and that sort of thing. But anyway, yeah, they were transporting their water through lead pipes. And so did we in the past. Houses up until sort of the 1970s in the UK had lead pipes in them. So you might think, oh, is lead a problem of the past? It's no longer a problem today because it was made illegal in the 1970s. Well, that's not true, because in some houses that were built in the 1970s and before, this lead might still be there. But why, you ask? Why is this lead still in my house? It's because the water company only owns the pipe from the water treatment works to the boundary box, to the pavement outside your home. And it's actually the householder's responsibility, and the pipes belong to the householder from the pavement and all inside the property. So it could be that the water company no longer has lead pipes in their system, but actually within a customer's home, there can be lead found. This is in addition to lead fittings and fixtures. So it could be that an alloy has been made. So you've got maybe some nuts or bolts, maybe your taps have got small amounts of lead in them because they are cheaper. They are not allowed by regulation, but they definitely are cheaper. And if you're using a non-water safe plumber, it could be that these parts are being fitted in your home. So there are still lead incidences in people's houses. On both a World Health Organization, an EU and a UK level, there's some really strict guidance, some really strict regulation about the amount of lead that you're allowed to have at the customer tap. I don't think lead is an issue at all at the customer tap because water companies try so hard to solve it. So even though they don't own the pipes within your house, they have to still make sure that the water coming out of your tap is safe. So this is why phosphate is dosed. So phosphate forms a protective layer around the inside of those lead pipes. So none of that lead can get in contact with the water and then enter the water body. And you know what? It really works. It really does the job. We have such strict lead levels that are allowable in this country and such great compliance. So why is it that I've got so many disadvantages of this? So phosphate is quite expensive. It's one of the most expensive chemicals that is dosed for water treatment and distribution. That's of mild concern. Water companies are very happy to pay this amount. Another concern is that phosphate, and this is the biggest concern for me really, phosphate is a finite resource, so it's mined rock. And some sources say that it would be gone in as little as the next 50 to 100 years. We've got no real as efficient alternative right now in this country to phosphate to protect against lead pipes. And this is a real problem. It's just going to be gone one day. And because of the costs, as it's getting more and more finite, the expense is going up and up. There can also be supply and demand issues. So a few years ago, a lot of our reserves were coming from China, and there was an earthquake in China, and all phosphate rock mining was stopped for the foreseeable future. And the price skyrocketed; it tripled overnight of phosphate. And water utilities had they couldn't do anything; they just had to pay this amount of money. It could be said that it's difficult to do dose optimization as well. So I mentioned about the lead in people's houses. Approximately 40% of households contain lead pipes, but just to be safe, we dose phosphate at all houses just in case there is any lead there. So like I said, you might not have lead pipes in your house, but you could have lead fittings and fixtures somewhere within your home. So even if you've not got lead, you will have phosphate. So that makes it really difficult to optimize that dose, because you're dosing at a water treatment works for a large number of houses. Another problem with phosphate is one of the building blocks of life. So what that means is if it gets into local water sources, it can cause mass algal blooms. You can see in the picture in the background a really nice green river. Well, that's actually eutrophication. So what's happened there is this algal bloom has happened on the water surface, and it is likely that all the other organisms within the water will die. So for instance, the plant life and then the fish, that sort of thing. Also, these algal blooms can be toxic. So I was having a walk before lockdown around Rutland Water sometime last year, and there were signs up saying don't take your dog off the lead because there's blue-green algae and there's toxic algal blooms, and if dogs consume the water, they could die. So they can be toxic as well. And this is the reason why sewage treatment works aren't allowed to discharge this into the environment in any way. Accidents could happen with water treatment works, but I think the most likely way of phosphate getting into the local environment is through pipe leakage, and pipes do leak. So what this means with the sewage treatment works is that water companies are paying to put this phosphate in the water to protect against lead pipes. Then obviously, as that same water is going down the drain, sewage treatment works are then having to pay large amounts and put a lot of effort in to getting rid of this phosphate. And sewage treatment works are really good at removing this phosphate. There's some really strong EU regulation against it, but it's just an extra cost. And when we're looking at making everything more circular economy, making everything fit together, this doesn't really fit. It doesn't really quite make sense when you think about it. So those are big problems surrounding phosphate, and I think it's a really, really interesting one, particularly that of it being a finite resource. I think that's a real big motivator to potentially stop dosing phosphate, and instead of having that phosphate dosing in place, trying to locate and get rid of all this lead. That would be the ideal situation, really. And one more thing that can be added. Now, I like to add this one because it adds a bit of controversy, and I think it's just a really interesting talking point, is that of fluoride. So fluoride is added to approximately 10% of UK waters. And it's a really interesting one because it's not the water company who pays for it to be dosed, who decides for it to be dosed or decides the dose at all. It's the local water authority, the local authority, the health authority. So it's a really interesting one. It's dosed to protect people's teeth against tooth decay, and has particularly found to be helpful in poorer areas of the UK. However, can you get too much of a good thing? Yes, you can. Fluorosis is discoloration of the teeth if you have too much fluoride. And actually, I've actually got this on one of my front two teeth. It's like you might see it on some people. It's a small white patch on someone's teeth, which is an indicator that it's minor fluorosis. So I've actually got that because I had braces when I was in primary school, and I would wash my braces in a fluoride-based solution, and then the instructions said to wash it thoroughly to get rid of this solution before putting it in your mouth. But I was in primary school, I was like in year 4 at the time, so I just put this thing straight into my mouth for sort of 2 years. So that's how I got mine. But yeah, it is interesting. So fluoride is most helpful for you when you're younger, when your teeth are developing, and it's not really of much use in adults. So the dose is controlled in tap water. But one thing that's not controlled is how much water people are drinking in areas where they've got fluoride in their tap water. One person might drink 8 litres of water a day, the other person might not touch a drop. So it's really difficult in terms of making sure that people are getting the amount required for them as an individual. It also can be found in toothpastes, in mouthwashes. So there might be one individual who's drinking a lot of tap water, who has toothpaste, who has mouthwash that have fluoride in, and they're getting an awful lot of fluoride when there might be people out there who are not getting it at all. One of the reasons why I enjoy talking about fluoride is because of the conspiracy theorists out there. So apparently fluoride was first dosed in Nazi concentration camps to see the impact. So the theory at the time being that fluoride was a mind-controlling substance. It's actually a natural substance that comes from rocks, and there are certain countries, for instance India, who have really, really high fluoride concentrations. Anyway, so the conspiracy theories suggest that fluoride is being added to people's water to dumb down the population and sort of control their minds. So I do not see the theory behind that. I definitely see how we are dosing this fluoride and we're not controlling the amount that we're dosing. But in terms of mind control, I definitely think it's improving people's teeth. I don't think we're trying to control people's minds. But yeah, really interesting one to discuss. And I love looking up forums about this. Sometimes people tweet me about this, and I just love having discussions with these people and finding out more information. So yeah, fluoride is an interesting one. Another thing that doesn't quite make sense to me in terms of our fluoride use in the UK in tap water is that there are alternative methods of dosing fluoride out there. So I've already mentioned mouthwashes and toothpaste having fluoride in, and that makes a lot of sense to me, particularly because you can target the people who need it most. Say, for instance, you can target people who have got tooth decay and say, well, if you've got tooth decay, you should buy this toothpaste. Or you can target children who need it most. Equally, other countries have different ways of doing things that I think really make sense. So some sources say that less than 1% of the water that is produced is consumed by people, is drank by people. So some councils are paying for this fluoride to be added to people's water, and then they're just using this fluoridated water to wash their car, to bathe in. It's not having the intended purpose. Apparently some areas in Germany, they give fluoride tablets to adolescents and children, and that's how they get their fluoride. In Canada, in some areas, they have a fluoride day at school. So what will happen on like a Friday lunchtime is after dinner, they are then given like a little amount of fluoride, and they have to rinse and spit. And that's just the norm. I was absolutely blown away when I heard that. I was like, that's so cool. In Russia, I think is the most ingenious one I've heard of. They put fluoride in their milk. So I think that's a great way of doing it, because unless people are like bathing in milk, all of that milk should be being consumed, in which case all that fluoride is being consumed as well. And also you had the argument that, you know, it's most likely children who will have a full glass of milk, whereas adults might only just have a splash in a cup of coffee. So yeah, I really like that. So fluoride is a bit different. It is added to drinking water for distribution purposes, but it's not added in any way to have an impact on the quality of the water and to maintain that quality through the pipes. I just thought I'd add it because I think it's really interesting. Maybe that's just me, but I think it's really interesting. So, are there any countries that are chemical free and compliant? So we've got Anglian Water there in the UK, and that's actually my office that I've highlighted on that map there. And then I've looked into there are some other places, some other companies in other countries who use fewer chemicals than us. And it's about the business aim, really, looking at these different companies and seeing how we personally can improve our water. So the companies chosen are these three. So the reason why they've been selected is because BCS in Denmark is 100% groundwater in its source water type. So one thing I was told quite a lot when I was speaking to people about this research, I was speaking to operators, I was speaking to people in the water industry about chemical-free water, is that they were saying that it's not possible in the UK, in Anglian Water, because the majority of our water is surface water in source, so it's coming from things like rivers. So the reason behind this is things like rivers are exposed to the seasons, they're exposed to big temperature changes, there are different things going on there, different nutrients circulating in the water, whereas groundwater is being extracted from deep within the ground, so the water quality doesn't really vary all that much over the course of a year. It's seen as very good quality water for the most part. So that's what people were telling me. And this company in Denmark, really, when people were telling me this information that it's not possible in our area, they were thinking of countries like this, where they're 100% groundwater in their source. They've never used chlorine, they've never used phosphate. That's what people were thinking of. However, these other two companies, these other two countries, are really interesting because they have a much more different split in their surface to groundwater. They have proven that you don't necessarily need phosphate, you don't necessarily need chlorine to produce that same water that we're looking for, but they've got very similar breakdowns of surface to groundwater, and yet they're not using these chemicals. So that's really interesting. The other thing I wanted to show you about these comparisons of these different companies is, at first I was really shocked by the leakage rate. So the UK leakage rate is around 15%. So that means of the treated water going out into the network, approximately 15% of that water is lost to the environment. So for the UK, 12% of Anglian Water is seen as good. Now, you've got here PWN in the Netherlands with less than 4% leakage. That's amazing. That's a big difference, and that's the first thing I saw when I looked at this work. However, then you look at the pipe length. So if you look at that pipe length column, the distribution network, the pipe network length, the difference is staggering, really. You see there around 1,000 kilometers in Denmark, in VCS in Denmark, where in Anglian Water in the UK, 38,000 kilometers. You know, that's a massive difference. We've actually got enough pipes in the UK to go to the moon and then back, if it's water and sewage pipes. We've got an awful lot of pipes, and you can really see here the challenges that we are facing as a company, as a country, before we can start even thinking about turning off these chemicals. So I looked at this data and I spoke to some people from some other countries about their chlorine use, about their water treatment, about their water distribution. And I came up with like a list of what the network looks like that's ready to go chlorine free or ready to go chemical free. And these are just some example parameters from that list. These are the sorts of things that we need. I went to a steering group meeting. I have these big steering group meetings every 3 months with academia and industry. I've got one tomorrow actually, so I'm quite nervous about that. So I have these big meetings with loads of people around the table, and we're discussing this. I'm showing them this research, and I was asked a question that I could not answer. So the question that I was asked by Robin Price, who's head of water quality at the time, great guy, was, if we had this perfect network, could we turn off the chemicals today? So I showed them all the attributes of the perfect network for receiving chlorine-free, chemical-free water, and this is the question that was asked of me. And my answer was, I genuinely have no idea. Even if we had this perfect network today, it had no leakage, it was next generation pipe material, could we stop dosing phosphate and chlorine? I mean, physically, yes, it's possible, but to achieve that compliance at the same time, I had no idea what the impact would be on people, on public health. I did not know. So this is where my experimental work for my PhD really began. And you can see me top left. This is the pipe rig at the University of Sheffield in the basement. That's where they keep the scientists. There's me posing with a pipette, being a STEM ambassador. And there's me sampling some sludge. Really, I should have had my hair up, but it was just for a photo. I wasn't actually sampling any sludge at that moment. So if we had this network, could we turn off the chemicals? So that was going to be my question. I'd finally decided, I'd pinpointed something that I was interested enough, and it was a big gap in our understanding, and this is where I wanted to focus some of my work. So this is what it looks like. So at Water Treatment Works, I wanted to get a feed of water from before phosphate and chlorine were dosed, and then I wanted to get a feed of water from after phosphate and chlorine were dosed. And I wanted to make a fake distribution network, a fake customer tap, to see how these two systems were changed in their water quality. I wanted them to run to waste, obviously, because no one's getting their chemicals turned off. I would love to do some experimentation with that, but I definitely don't think I'd be allowed. And in addition to this, I was still interested in this whole groundwater, surface water debate. So I actually had two lots of these systems designed and built. So one of these systems is on a groundwater site, and which should be more biologically stable because it doesn't have that much variability. And one I wanted on a less biologically stable site. So I've got one on a surface water blended site, so a good mix of nutrients, of microorganisms coming in there. So I've actually got two of these systems to test out this question and to actually find out the answer. So this is what the system looks like. It is a shipping container, as you can see. You walk inside of it and there is a wall of pipe on the left. There is a wall of pipe on the right. There's also some really interesting technology in there. ATI, they provided me with some instruments that give me live water quality data, as well as informing me if there are any problems in my rig. So that is really interesting. Boltings Limited and Chemical Support have both helped design and build this rig. Chemical Support built it all, so that's really cool. So you walk inside this shipping container, wall of pipe on the left, wall of pipe on the right. The one on the left, they're both completely separate from each other. The one on the left has this feed from after chemicals are dosed, so has chemically treated water in it. The one on the right has a feed from before these chemicals are dosed, so is chemical free. So I can directly compare what is going on in these two separate pipe networks and at the two separate customer taps. So I am a microbiologist in background, and I've got three basic questions that I'm answering. The first one is, who is there? So for that, I'm looking at normal plate counts that we would normally do, things like E. coli and coliforms. I'm also complementing that with some DNA sequencing, which is not a normal thing that we would be doing, but it's looking at what organisms are able to survive in these different pipes in these different locations. Or not looking at who can survive, looking at what is there really, if it's there, if it's not, presence or absence. Then there's how much is there. So this is all about quantification, counting the numbers. So for this, we're using flow cytometry. Flow cytometry, it's a machine that uses lasers to count individual numbers of cells. So I can look at a sample of water and I can tell you the exact number of cells that are in that sample, as well as the number of intact cells. So cells that are fully intact, have their cell membrane intact, which means sort of viable, living. So you've got like a count of what's alive, a count of what's dead. So that's really useful information, because it could be that my E. coli plate counts come back as 0, but then my flow cytometry counts come back as thousands. So that's really helpful. And then I'm looking at what has the potential to be there, so what could grow in future. So for that, I'm looking at a whole suite of nutrients, things like carbon, phosphate, sulfate, nitrate, various metals. So that's normal water quality analysis that we would normally be doing anyway, to see what has the potential to be there in future. So that's the work that I'm doing. So in all, there's me in my shipping container. This is actually on site at Chemical Supports. This is before the rig was on site at Anglian Water, because if it was an Anglian Water site, I would definitely have steel cap boots on a high vis, just for a start. That's just to point that out. So I've got two of these systems. When everything gets back up and running, maybe you could contact me, or maybe you could come have a look. Might have to be some time, but I'm always welcome to show people around. So that's just some information about the rigs themselves. I'm aiming at a 2 to 3 day residency time within my rig, because like I said, that's sort of the average for the areas that I'm looking at, the networks that I'm looking at. I'm complementing my rig samples with samples at the customer tap to see if what is happening in my rig is similar to what is happening in people's houses at their actual taps. So yeah, grade P 100 HDP pipe is what I have determined to be sort of next generation of pipe. It's been fusion butt welded for this project. I've learned an awful lot about engineering. Then when I started this PhD, I didn't realize how many valves there were. I didn't realize how many times pumps could fail. It's been a real steep learning curve, but I've learned an awful lot. And you can find me most days, normally outside of lockdown, in one of these containers in some way. Now, biofilm. When you wake up in the morning and you brush your teeth, there can sometimes be like a sticky substance on your teeth. Now, please say that you have this as well, because otherwise I'm definitely not cleaning my teeth okay. Now, this sticky substance is actually biofilm. So this is like a sticky spider's web of all sorts of different microorganisms. And this sticks on the insides of drinking water pipes as well. And it's how organisms stay within the network. So this image is an SEM image. It's a type of microscope that you can actually see this form under the microscope. As you can see, it's quite patchy. It's not a uniform, slick inside layer like phosphate is. It's a bit here, it's a bit there. Again, it's like cobwebs on a wall. So that is biofilm within pipes. Now, I have got, so one thing I really wanted to make sure I had on my pipe network is also have analysis, not just of the water running through the pipe, but also to look at what's going on the pipe wall, particularly as the pipe wall has been in place for an elongated amount of time, like 6 months, to see how the water and the pipe wall are interacting. And if anything nasty is growing on the pipe wall, that is then entering the water course when I flush it, when I do a fake burst event, for instance. So I've got these small black, I call them coupons, and they're a bit like a cork in a bottle of wine, in that you can pull them out. I get a very high-tech device, otherwise known as a toothbrush. I brush off the material that's grown on the pipe wall, and then I can either use SEM, the microscope, to see visibly what has grown, or I can run it for a flow cytometer to see like the numbers, the amount of growth, or I can do DNA analysis. So I'm not just looking at the water itself, but I'm also looking at the pipe wall. So to do this, I have to turn the flow down, I have to turn the pressure down, and then I extract my coupons. So overall, I am hoping to provide Anglian Water with what steps they need to take if they want chemical-free water to be possible in the future. Now, this is just an example image. This isn't everything I'm suggesting. So, for instance, if we had that perfect pipe network, what additional steps do we need to take? If we just stopped the dose of chlorine and phosphate, would there be an increased risk to public health? Would we breach compliance? We really need to understand our network, understand how treatment works, networks work, to be able to get the confidence needed to turn off these chemicals. And I really hope to be a part of that. I'm in the last year of my PhD now, so everything is coming together nicely. I'm doing a lot of writing right now, FYI. So thanks very much for listening to my presentation. In summary, why are we doing this research? Because chemicals can have unintended consequences. Is it possible? Yeah, I believe so. There are countries who are doing it. They're doing it every day, and we've got a lot that we can learn from them. And is it possible here in the UK? We do have a lot of challenges to overcome before it's possible. I think definitely our leakage is of concern. Our massive network, I don't really know what we can do about that. It makes pipe replacement difficult. It makes us have an aging network because it's so difficult to get around to change it all. Definitely legislation changes have to be made, because the whole customers owning the pipes just within their homes, that causes all sorts of problems. But my future research will determine the next steps that the UK has to take before we can become chemical free. So thank you very much for listening to my presentation today. I hope you enjoyed it.
Thank you so much, Natalie. That was great. And judging from the number of questions, I know that everyone else enjoyed it just as much as I did. So we have a few minutes now. I'm going to kick off with some questions, and I'll start with one. I'd be interested in understanding how COVID-19 has affected your research, specifically with your rig, over the last couple months.
Yeah, thanks for your question. So it's been difficult for everyone, hasn't it? I think you've really got to think about how lucky you are, and rather than focusing on the negatives. So my plan for my research was on the 9th of July, I got my pipe rig up and running. I was so excited, I was so happy. And the plan was to have it running for 6 months before then doing this flushing to mobilize what had grown on the pipe wall and get it into the bulk water. However, since lockdown began, my experiments have been shut down, which does mean, unfortunately, that all my growth within my pipe wall has died. It's a bit like a plant, you know, you've got to feed it, you've got to water it. So it has died. So my plan is, after lockdown has been lifted and it's definitely safe for me to be on site, and it's safe for the labs to analyze some of my samples, then my plan is to disinfect and start again for 6 months. So some of you who might have listened to me speak before, you might be thinking, this is like a never-ending PhD. It really is, because I've had to stop my rigs and I'm going to have to restart them. So yeah, that is the plan. I do intend to finish the PhD, to get the research. I work very hard to get these rigs up and running. So yeah, that is my plan going forwards. But safety is of my primary concern, really.
Great, thank you for that. So the next question is, can phosphate be recovered at the sewage treatment works and recycled back into the appropriate form to be used in the treatment process?
So definitely yes. In terms of phosphate recovery at water recycling centres, so one of the main applications of phosphate is actually as fertilizer, and that's one of the ways that it gets into most water bodies. That's how they get eutrophication is from that process. So there are lots of EU-funded projects going on about phosphate recovery at water recycling centres, but they've not really been using that to use it for water treatment purposes. Instead, that phosphate has been used to send to farmers and to apply as fertilizer. But in that way, it's freeing up phosphate to go straight to water treatment works. I think, especially in this country, that there's a big fear of sort of uniting water recycling and water treatment processes. And that's not from an industry perspective, I think from a customer perspective. So I think that recycling idea, it does frighten people. But we've been giving it to farmers. So at least some aspect of the circular economy is definitely coming in there.
Thank you for that. So the next question is, why is leakage a factor in chemical-free drinking water?
I think for me, the reason why leakage is so important is because of pipe ingress, so contaminated pipe ingress. So if you think about it, if water is leaking out, it must be because there's some sort of hole in the system. And when pressure's changed, that hole can work in reverse. So instead of water leaking out, environmental water can be sucked in from, say, the soil, and that can contain contaminants. So if you've not got chlorine residual in your network that's trying to kill off microorganisms, it could be that you're getting that contamination, new pathogens entering your system from the environment that could then be transported to the customer tap. And I think it's a big concern of that not being picked up quickly enough. So right now, today, we're using plate counts, but they have a long turnover time, like 12 hours, 24 hours to get the results of that back at the customer tap. Whereas flow cytometry, it's really quick, it's really instant. So I think it's a combination of right now not having that real-time result at the customer tap to identify pathogens like that coming into play, because we're doing the testing at the final water of the water treatment works, but it's really difficult to monitor the quality of the water within the pipe network. So yeah, it's really about getting rid of that contamination from environmental water sources.
Thank you. So the next question is about what you mentioned about climate change affecting source water. Is this because the river levels will be lower and drought more likely?
Yeah, it can be because of that. So I definitely remember a few years ago we had some droughts in the UK in the summer, and the reservoir levels were getting really low. And it might seem that there is, for instance, I don't know, say 30–40% of the water left in the reservoir. So when you're looking at it, like walking around the res, you're like, oh, there's loads of water in there. But yeah, as the water levels drop down, the quality can really decrease. And then there's also the concern of groundwater. So groundwater percolates through layers and layers of rock over many, many years' time. But if we're abstracting more water, that's getting down to the ground. It could be that we're running out of our groundwater sources.
Perfect, thank you. So the next one is it important to monitor phosphate and nitrate in the distribution lines, or is it more important to monitor these levels before disinfection with chlorine?
I think that's a good question. So for my research, I'm definitely monitoring phosphate and nitrate within my pipe network and at my customer tap, purely because it's a food source for microorganisms. So I think it's really interesting what we're doing. So we're applying chlorine to try and kill them, and then we're applying phosphate, which is food. It's really confusing. You know, we're doing the opposite of that. So for my experiments, it's really important as well to try and see what sort of microorganisms are growing, because certain organisms really like the taste of phosphates. They grow and thrive on phosphate. But other organisms might come into place when that phosphate is really low. So for me, it's really important. But I think for water treatment and utilities today, I don't think they've not got that same level of detail as what I'm looking for. So I don't think it's that helpful for water companies today. Definitely useful for my research, but not so useful for wider water utility. One thing that I do think would be interesting to do, and it's an experiment that I'm really interested in actually, is water companies do monitor phosphate at the customer tap. I would be really interested to see how much of that phosphate we're dosing at the water treatment works is ending up at the customer tap. You know, is it all being used to coat the lead pipes, or is there some presence there? I think that's a really interesting question.
Thank you very much for that. Thank you so much to everyone who submitted questions. There are still a few we haven't been able to get to, but just conscious of the time. So as you can see, Natalie's put her contact details at the bottom of the screen, her email address and Twitter handle. So if you want to go ahead and get in touch with her if you have any more questions. And I'm going to wrap up the webinar now. So thank you very much, Natalie, and thank you very much everyone for attending our webinar, Chemical-Free Drinking Water Treatment and Distribution. Once you leave today's webinar, you'll receive a survey on the presentation, and it would be great if you could complete that and provide some feedback. You'll also receive a follow-up email in the next couple days with a link to view the recording of today's webinar. On behalf of the Institute of Water and on behalf of Natalie Lamb, our presenter, thank you very much for joining us and enjoy the rest of your day.